Okay, hi, welcome to lecture 20 of quantum physics for non-physicists. And today is the 19th of November. And today we will continue with this new topic of quantum thermodynamics. So in particular, we will start to explore the thermodynamics of computing and in particular quantum computing. So we'll see what is the relationship between all these concepts of work and heat and energy and things that maybe you're more interested in, like information processing and computing. And we'll also start very slowly with the idea of heat baths. So our daily analogy today is coming to us via Facebook from a friend of mine, Lídia, who is a researcher in quantum foundations. And she has this analogy in her thesis of being like a diver, which I replaced with a dolphin because they're easier to draw. So a diver that wants to go underwater and play with things like the algae, the fishes, etc. But every now and then you still need to come to the surface to breathe, like a dolphin does. Okay. And this is a nice analogy, or at least a beautiful analogy, for this separation that we make between the classical world and the quantum world. Okay, so we go underwater and we play with things like unitary evolution of quantum states, even when we model like a pointer explicitly and measure and model a measurement like an explicit unitary evolution. But eventually at some point, because this is not our experience, right? In the same way that underwater, like water is not what we breathe. In the end, at some point, we'll need to come back to the surface to something that is classical outcomes and that we can talk about like probabilities of getting different outcomes, right? So this is where we make this kind of cut between the quantum world and the classical world. And yeah, maybe, there's other animals that can breathe water. Maybe one day we'll be able to model like everything in the underwater view in the quantum view. But for now, we still need to make this approximation, which is to come to the classical world to relate to our experience. Very good. So there is some housekeeping, but it's a bit confusing, so I'll send you an email. The short version is that the lecture notes are online now, so please send some comments in the first few lectures are covered. And the second one is that apparently some strings were moved and you might be able to get credits for the Masters in Computer Science already this semester through some methods. I will send you a copy of this email. And the other news is that, again, strings were moved in the legal side, and very, very soon, maybe already next week, maybe the week after, you'll be able to have this tutorial of quantum programming. And then we have planned some exercises to apply actually some of what we'll start looking at today in quantum programming languages. Okay. So what did you do in the last lecture? We started thinking about how to model things like an energy battery at the quantum level, right? And we saw that we want something like a Hamiltonian that looks like a staircase, right? With very, very small energy gaps, that's this delta. And we want it to be in a state that is as close as possible to a state of energy EK, because this corresponds to this idea of having a weight lifted at a certain height that then can lower and use this energy, right? If we take this to the continuous case, then we have something more like a particle in a line. You can even think of this as a line like X, and now we just put it vertical. And now we can really think that if you have some object up here, then it has more energy than object down there, just from just like the gravity. And now, of course, we cannot have states like a state like this, because that's not a physical state, but we could have something like a little wave packet around here, like a little Gaussian around some energy, right? So then the Hamiltonian of this would be exactly like so if you replace this E's by X, then this would be like the X observable, okay, except now the basis, our favorite basis, we just call it E basis. Okay? So it's exactly like the limit of this in the continuous limit, where we make these gaps very, very small. Good. And then we saw how do we use these batteries? Well, if you want to account for the energy cost of doing some operation in another quantum system, then what we do is to apply an energy conserving operation in the global system of thing we want to change in our battery. Okay, and then we demanded that this global operation is a unitary that commutes with the total Hamiltonian, where the total Hamiltonian was just this Hamiltonian of the battery plus whatever Hamiltonian our system of interest has, right? We saw the case of a qubit there. And we saw that from this condition, if they commute, then there's no change of energy overall in the global system. So we do an operation like this. This is exactly what we saw. So we lower the system from the, for example, from the 1 state to the 0 state, then we have to raise the battery, right? And this would be an operation that gives us energy in the battery. Okay, so then we just measure the change of energy there. And what was not present in this example, but there'll be next week, is that some of these operations may not just change the average energy, but they also might change the variance. So meaning that we start with a very good state that was like a state like really here, or in the Gaussian case, like a state that was very narrow. But due to this operation, it will be a bit more spread out, right? So then it becomes a bit less useful as a battery because then we don't know exactly how much energy is stored there. We don't know how many times we can use it until it's there's no energy to draw from there. Okay? Much like if you have an AA battery at home and you don't know how long it has been running in your remote control, I mean, you wouldn't put it in a very essential device that absolutely needs energy, right? Okay, so this is what you've done so far. But so far, this was all very, very, very simple. And now we want to answer questions that are a bit maybe more interesting. So one would be, since you're talking about thermodynamics, how small can fridges be? And if you say fridges, you can also say heat engines, which we'll go into next week. But I thought we might start with another question that maybe is more close to you in computer science, which is, must computers always heat up? Must computers always dissipate heat? And this is what we'll explore today. And I mean, as a warning, today we'll really, really just start more with motivation and approach, and we will not solve the problem today. Okay? So the question is, how much heat must computers dissipate? And analogously we'll see later why it's an analogous question, but it's the question of how much energy must computers consume, how much electricity must they eat up to do some computation. So first, we need to know what we mean here by computers, and then we'll need to know what we mean by heat and by dissipating. Okay? We need to make all of these concepts clear. So let's start with computers, and let's start with just quantum computer. And the first thing we need to see is how we model these qubits. I mean, we know that there are Hilbert spaces that correspond to, just 2 basis states, right? But they need to have some kind of Hamiltonian, right? So what's the Hamiltonian of a qubit? In principle, it could be anything. And this will depend on the actual implementation of the quantum computer. It's also the case for classical computers, right? In the end, like your bits are encoded in some solid state hard drive, or they are encoded in a magnetic disk or a floppy disk. So in the end, like there's a physical system, and physical systems have Hamiltonians. But the simplest case, let's look at the simplest case is just saying, well, this Hamiltonian is 0. And this corresponds to what? Well, if I write here the energy and I draw here the 2 states, this is the state 0 and state 1, they have the same energy, okay? As opposed to having, like we saw in the example earlier this week, that we had this state 1 a bit raised, so the Hamiltonian was epsilon times state 1, right? But so let's look at the simplest possible case, H1. So in this case, some terminology physicists use is something like degenerate energy levels, where energy levels is like eigenstates of the Hamiltonian, that's all it means, and degenerate just means they have the same eigenvalue. Okay, in this case, the eigenvalue is 0. But then you may ask, well, how can you apply operations if there's nothing there? And the idea is that although they have the same energy, in order to go from one state to the other, in order to apply operations like the X or the Hadamard gate, you still need to do something non-trivial physically. So one model for this is, these things are studied in the QIP2 course, so I will not go into any meaningful detail here. But one idea is to try to come up with a physical model, a physical system that resembles a bit like what we saw, where there's a potential barrier between two boxes. And we say, well, if the particle is in this box, this corresponds to state 0. If the particle is on this box, it corresponds to state 1. And what an X gate would have to do to go from one to the other, right? This would be the X gate moves from 0 to 1 and vice versa. It needs to kind of either lower this energy barrier, wait some time, and then raise it again, for example. Okay. So if you want to look at implementations of quantum computers, I recommend the course QIP2 in the next semester. Other examples, it's like in trapped ions, you have like the internal degrees of freedom of some particle, which would be an ion, and some of them are like almost degenerate. This corresponds to essentially like the spin of an electron being up or down. And then you have like, this would be your 0 and this would be your 1, and this energy gap would be very, very small. Yeah. We don't know yet what energy levels of atoms and ions are. We don't even know what ions are. But so this is something that we might look into towards the end of the lecture if we have time. But if not, don't worry, you can do it in the QIP2 lecture next semester. Right? But the idea is that in the simplest case, we can indeed make this Hamiltonian being 0, so that having the qubit in state 0, having the qubit in state 1 has the same energy. So in this case, in the model that we saw before, okay, that we saw in the previous lecture, any unitary on, even if you have an explicit battery, any unitary on S, in the end is going to commute with the Hamiltonian, because, okay, so if you have USB Hamiltonian total, so this is going to be USB age of the system times identity on the battery plus US. Well, let's just write down what USB is. So it's US times identity on B. And this is US times identity on B, identity on the system times Hamiltonian on the battery, right? But, well, this one is 0 because they act on different systems, right? You have US acting on system S and HB on system B, so they are operators in different systems, so this is 0. And in this case, well, this HS is 0, like we saw before, so the whole thing is going to be 0. Right? This means that any US can be implemented for free. Now, of course, that let's put for free in terms of energy of the battery. Okay, the energy of the battery in the beginning and the end is going to be the same because if you apply this US, it does not change the energy of the system because it starts with 0 and will end up with 0. So you don't need to go up and down in the battery, right? So this could even like include something like some very complicated, I don't know, unitary, like very complicated circuit where we have, I don't know, 3 qubits in S and they do a series of operations, taka, 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 something. It doesn't matter exactly what, right? Of course that there are hidden costs here, okay? So for example, like we saw before, to apply US, in the end, this gate needs to be some Hamiltonian that we turn on and off. So there needs to be some kind of control system, a clock that turns this Hamiltonian on and off, etc. And this might cost energy on its own, but it's like kind of in a different part of our hardware. And for that, we will see this. We'll see details of this in the course Advanced Topics in QIT in the next semester, if you want to go into this. But for now, at this level, we say, well, reversible computations for now come for free in the sense that they don't waste energy, they don't change the state of the battery. Okay, come for free. And indeed, if after running all this unitary, you want to just, maybe you started with qubits in state 0 and you want to do some other computation, then all you need to do is to reverse this circuits, right? So you can apply U on S, and then you can just reverse it. So apply US dagger, and then you'll end up with the initial state. Right? Okay. So these are reversible computations. We say for now, we consider them for free. What about irreversible computations? So what's an example of an irreversible computation? You could think of something like an AND gate in classical circuits where you have some X and you have some Y, and then you end up with X dot I, right? So if there's 1 0 between X and Y, this result will be 0. If they're both 1s, then this is 1. Yep. Well, the nice thing is that we can always implement them in a reversible way by adding some more wires. Yeah, so we implement this reversible. With some memory cost. So in this case, we could put like X, Y, and then apply here a reversible gate that returns their X, and here X dot Y. If we have this too, then you can go back. This is the U. From here, there's a reversible, there's the reverse that you can apply, and this also applies to the quantum case. Okay? If your X and Y are either 0 or 1, it's a nice exercise to see what is the gate that does this, but there is a gate. Okay. But so what if you don't want to reverse it? I mean, I want to keep my X at the end. Okay. So if I want to keep my X at the end, this is the thing that I'll use for, I want to keep my XY at the end. This is what I'll use for other computations. I'll plug it in somewhere else, like in the rest of my circuit, I don't know. But I don't need this upper register anymore. And eventually I'll, I don't want to end up with lots of garbage wires in my circuit. Eventually I want to use it again for something else. So I want to do something called erasing this, which means that I want to end up with a nice zero state. Think of it like formatting this this hard drive, or this wire. Another example of a computation. So if you didn't need to store, by the way, if you didn't need to store this somewhere else, then all is good, because then you can just reverse with this U dagger and the computation says again for free. But if you need to store this somewhere and you want to eventually get rid of this one to use it anew for some other computation, then this will have some unknown cost, right? Which we don't know yet. Another example is measurements. Right, so you have your state psi, and then I want to measure it, right? And what do you see that measuring is? Well, so this is a measurement where at the end I get some classical outcome. But we saw that measuring is, I bring in psi, I bring in some pointer, maybe in some state 0, I apply something like a C naught, and then at some point, like this is a very large system and becomes kind of classical, right? So it's like I measured this one instead of this one, which means again that at some point I'll end up with some garbage that I want to erase. So at some point I want to erase this and bring it back to 0. Yep. Okay, I have a nice analogy about this, but I'll leave it for next week because I'm running out of analogies. Yep. Okay, but the idea here is that like every time I want to measure a system, this measurement is not coming from the sky. Well, what I need to do is to bring in a very nice pointer in order to implement it physically. And at some point I'll run out of very nice pointers and I'll have to erase everything again. Okay. Or maybe there's a work cost in creating the very nice pointers in the first place. We don't know this yet. So it seems like in these two examples, it boiled down to the problem of erasure. So overall, in general, we can always think of any irreversible operation. And this means an operation that is implemented by some TPC, some quantum channel epsilon. We can always think of it as a reversible operation in a larger system, followed by some erasure, which means taking some ancilla from whatever state to the state 0. So look, this is the same as we saw before for channels, when we had the channel was traced over some ancilla system B, C of, we had our array times some state on C, and here would be some U AC, UAC dagger, right? We saw that the map on A that's irreversible can be decomposed by, we take this pure state in our ancilla, we apply a global unitary operation, and then we trace out C, right? And this is if we want to look at just what happens on system A. Okay, so in this example, it would be just what happens like here, for example, to this system here. But in this case, what's happening to system C is that it will end up with some trash, like with some mixed state in there. And eventually, if you don't want to keep buying memory for your computer every time you use it, eventually you need to format this memory. So you need to take whatever is left here after this unitary and reset it to 0. And that's the part that is the reversible transformation. So I'll give you a classical example. So of erasure. let's say we want to format a hard drive, which is in the following state. So we have some S, it's a bit string that you want to erase, right? And we know it's looking like this, like 0, 1, 1. I don't know what this fourth bit is. 0, 1, 0, 0. I want to format it, which means at the end of the day, I want to send it all to zeros. Okay. So what can I do if this is my knowledge of the state of the bit string? Then, well, whenever I have a 1 here, okay, whenever I know I have a 1, I'll just flip this one. So you get 0, 0, 0, I don't know, 0, 0, 0, 0. Okay, so flip once, and this comes for free because it's just a bit flip, it's reversible. So in our picture, it comes for free. But then I need to kind of still erase this 3 1, so go from some unknown state to the 0 state. And how much does this cost me? Well, it costs me the whatever cost is of erasing 1 bit times 3. And what is this number 3 here? So the number 3 was the number of unknown bits. In my original bit string S, which can be quantified by something called the entropy of S. It's kind of the definition of the entropy of S. And which, to be extra confusing, is also represented by H, in like the Hamiltonian and the Hilbert space in physics. Okay, you don't need to know yet exactly how we compute the entropy of something, but I just wanted to give you this idea. It's like we reduce the problem by things that we know how to solve. We flip them, this is for free, and it's kind of like a compression problem. I started with this, I compressed it for free via this reversible operation to something that is already in the desired state, and then a few bits that are unknown, and then I just need to deal with this unknown bits. So this problem is very close related to the problem of compression in classical computation. It will be quantified by something called the entropy of S. We'll talk about the entropy both in QIT course and in the advanced topics. For now, we don't need to deal with this because we're just going to worry about this part of the problem, like what's the cost of erasing 1 bit. But before that, we're going to look at the quantum analogues of this problem. So suppose that we have our quantum hard drive. So our little circuit is now in the state rho S, which let's say it's 5 qubits. And let's say we know that it's 0, 1 here, then something that we don't know very well, 3, 4, some stage. Maybe we don't need to specify it for now as here. So what we do like before, first we want to apply the free part. So we want to deal with the qubits that we know how to deal with. So we have this one here and this one here that we can flip for free. So for this, we apply the X operator. So what we apply overall, so we do nothing on the first. We do, so U, S, we do a poly X, so remember, yeah, on the second. We do nothing on the third and nothing on the fourth because they are complicated. We don't know what they are yet. And we apply an X on the last one. Yeah. So now we end up with 0, 0, 0, 0, row 3, 4, we don't know what to deal with. and 0, 0. And now we need to apply some kind of erasure protocol. Some map that takes some state row 3, 0 to 0 and 3 times 0 and 4. Okay. And then if we do this, then we'll end up with just zeros everywhere, which is exactly what we wanted, right? Now, so this step here is the one that we don't know yet how to describe, and we don't know how to implement it. So let's make it even easier. Let's look at the simplest possible example for this. Simplest example for erasure. Well, let's suppose we have only one qubit, and we want to take it from the fully mixed state, so the most mixed state we can do, to the state 0. So we want to take it from this to 0, okay? Where this, remember, this is just this state, which is 0, 0 plus 1, 1 over 2. Okay. So let's see if we can do this in the model that we have so far. Let's see if it's simple to do it in the model that we had so far, where we just have the system and the battery. So now let's draw it here. Remember, energy goes up. Here's my qubit. That's state 0 and 1. This is 0. This is 1. And it's originally in this state 0, 0 plus 1, 1 over 2. I didn't put a square. Good. Which is kind of a, it's like I have a little bit here and a little bit there. And now suppose I have the battery, which starts in a very nice state, EK, right? Okay. So my overall state, initial state is row 0 SB, is this 0, 0 plus 1, 1 in the system, tensor EK on the battery. And now suppose that I come up with some kind of unitary that does the job. So I don't know, one simple example could be that I just, oh, why would it go away? So I think one of my devices lost Wi-Fi. So let me stop sharing. Let's share again. No, it cannot detect it. Ah, there it is. Okay, we're back. Okay. Let me just see the chat. Okay. So suppose that we found some unitary that did the job. Okay. Maybe it's a unitary that just maps, I don't know, could just map EK to 0 and put this 1 somewhere else. But the problem with this is that if I apply this row USB, if this starts being, if this is a mixed state, then the final state is also going to be a mixed state. This can be made more precise if we start talking about entropies, but I didn't want to go into much detail about this. What I mean by this is that this uncertainty that we have here, okay, it will just get shuffled into the battery, which means that in the end we'll end up with a state of the battery that is not very useful for us because it will be exactly this kind of dispersed states in the battery. So then our battery becomes not so useful for accounting. So what this tells us is that somehow by doing just by using just these two systems, we can't really do the erasure on its own, not without like destroying our battery. So we need some other resource. And if this felt a bit vague, then when you see the actual implementation with a new resource, then it will become much more clear. So we need on our resource, and this is going to be this idea of a heat bath of some temperature T. So before I explain what a heat bath is, let me just give you a classical result that relates erasure to some kind of heat dissipation and energy cost in the classical world, which we will later recover here. And this is what is called Landauer's principle, and I'll explain you a little bit how it works. So I usually try to not include many names of physicists in this lecture. There's a reason for this, which I'll tell you at some point, but in this case, it is the name of the thing. So what it says is that erasing one bit of information, which means taking one unknown bit to the state 0, formatting one bit at some temperature T, and I'll explain in a second what temperature means, dissipates it some heat that is proportional to the temperature, and this thing here, it's called, it's a constant, it's called Boltzmann Constant. And it's very, very small, so just to give you some idea, this is orders of magnitude more efficient than the most efficient computers that are still experimental. They're not commercial. Is still like 2 or 3 orders of magnitude lower than the heat dissipated by those computers, because most dissipation is not, right now, it's not in computation, it's more in the transport of like electricity between different parts of the computer. But still, so it's like 2-3 orders of magnitude lower than the best computers we have today, and 3 or 4 better than the best commercial computers, which seems like a lot, but it's not like extraordinarily smaller. And this principle, if we can prove it in the quantum case, then what it does is that it creates this link between thermodynamics, like how much heat is dissipated, and something like computation, right? What's the cost of computations per bit? So I'll give you just a very, very toy example of how this works. And I will not make any computation now. I will not prove you that it works, I'll just show you, okay? And so suppose, there's many ways of encoding bits, right? So suppose now I have a box, and I'll have a gas inside this box. And if the gas is all on the left side, I call it bit 0, and if it's all on the right, I call it bit 1. And let's say we start with not knowing, well, the gas is just spread out throughout the whole box. Okay? So we have neither 0 nor 1, we just have total uncertainty here, but we want to go to a state where there's kind of a separation between, and all the gases here on the left, right? This should be our state 0. This is our goal. So it go from uncertain state to the certain state. It's like going from this question mark to 0. That's how formatting the hard drive in this very simple example would be. So one way someone suggested doing was this. Well, we just put a wall that can move here. Okay? And then we just attach it to some weight. This represents kind of our work, and we just lower this weight. But wait, we're not doing this in the vacuum. We're doing this, inside some room, and this room could be at some temperature T. And for a gas, the temperature relates to the velocity of the particles that are inside, that are outside here. So we do this very, very slowly, such that we pull this, and then we kind of let it thermalize, which means that the particles inside will have kind of the same velocity on average as the particles outside. So if you tried pumping up the tire of a bicycle, then you know that at some point it starts costing you, right, to fight against this pressure of the pressure of the gas inside, right? So that's the idea. Like the more we pull this in this direction, the more it starts costing us to do it. So we'll end up, and how much it costs us depends on the temperature of this gas. So we'll end up losing here, and there is some energy that is dissipated to our environment outside, and that we pay the cost by having to lower this weight. Now one can do some thermodynamic calculations and find out how much energy actually we lose in our weight, okay, from like this position to this position, and we can find out how much heat is dissipated to the outside, and it's going to be exactly the same, and it's going to be this, where this number log 2 just comes from the fact that we went from a full volume to half the volume. It doesn't matter too much what the specifics is, but I just want to show you that, okay, here's a toy example of how we can actually erase in a physical sense, and at least some intuition as to why this should dissipate heat and cost us some energy. Yep. Right, so the idea is that it gets harder and harder to pull as we kind of compress it more. Good, so in the quantum case, we don't want to do this. We want to go from like this 2 qubits mixed state to having everything on state 0. And also we don't know what temperature means in the quantum case. So this is the question for next time. So quantum case. What is temperature? And what is the equivalent of a heat bath? So these are the questions that we will try to solve next week. But first, let me tell you what a heat bath is classically. And maybe the best analogy is to think you have a cup of coffee. Okay. Here's your coffee here. And if you leave it outside and there's some temperature of your flat, eventually the coffee inside will cool down to this temperature T, right? And the thing that we call the heat bath is this thing here. And what are the general properties of this? So we'll go into more detail next week, but just to see what are the properties that we want to reproduce in the quantum case. So one is that, well, given enough time, it will thermalize most other systems that it touches, right? The same way that if you have a hot bath and you put inside like an ice cube, eventually it will thermalize the ice cube. And because the bath is so much larger than your system of interest, the temperature of the bath will almost not change, or you cannot detect this change. So it's this idea of having a much larger system than your system of interest that will thermalize it. and that will not change much in the process. The other thing is that we don't need to have a very detailed description of all the particles in this gas. We just need to know something like the temperature of this gas in order to know what will happen to my system of interest. So you only need like one macroscopic parameter. And the final thing that we'll need is that, and I'll explain this later, they are useless on their own. If all you have to work with is one heat bath, there's nothing you can do from it. You cannot extract work. If you could, then you could build a perpetual motion engine. So these engines that just create energy from nothing. So these are the properties that we'll try to see how to describe in the quantum case. Then once we have this, we will add it here, the heat bath, as a resource, and then we look into a global operation that does indeed erase the system, and we look at the work cost of this. So all of these ingredients are in order to solve the question of how much heat do computations work. So we'll do this, and then for the remainder of next week, we'll look into very small fridges of also a couple of qubits, and then we'll go back to more traditional quantum mechanics. Okay, thank you, and see you next week.